Hello, welcome to the last module of the logic course, which is about satisfiability modulo theories. In this module, we will first return to SAT and talk a bit about practical SAT solving, which is then the basis for solving more advanced reasoning tasks with expressive logics. So you have heard about first order logic, which is an extremely powerful logic and which provides you a lot of expressibility, but with the price that the reasoning becomes very difficult. And SMT, satisfiability modulo theories, is a compromise between the expressiveness and the hardness and the reasoning complexity. Yeah, but before we talk about this, let's return to practical SAT solving. In SAT solving, we are concerned with dealing with being able to solve the satisfiability problem. So we want to know if a given propositional formula is satisfiable, meaning if it has an assignment, if there is an assignment that satisfies the formula. In the first module, we have introduced the language of propositional logic and its properties, its semantics, and we also learned about the decision problem of propositional logic, the SAT problem. Here we ask whether for a given propositional formula there is an assignment to its propositional variables such that the formula evaluates to true under this assignment. Yeah? And when we are able to solve this satisfiability problem, then we can solve a lot of other problems which have the same theoretical complexity. Yeah? So this propositional logic and satisfiability checking can be used as a framework for which efficient tools are available. And then when we have an application problem, we take the application problem of the same complexity and translate it into a SAT formula and give it to a SAT solver which decides whether the formula is satisfiable or not. And in the following, I would like to talk a bit about efficient SAT solving and techniques that help to decide the value of a propositional formula. Yeah, with the value I mean whether it's satisfiable or not. And the first thing we have to consider is what does the input of a SAT solver look like, and in practice, the problems that arise from application tasks are often formulas of arbitrary structure, so we do not have a restricted structure like a conjunctive normal form or a disjunctive normal form as we have introduced it. But the problem is that this representation is often not so easy to handle. This tree structure we get for a formula is in principle representable by a suitable data structure, but this tree representation has several disadvantages. On the one hand, updates become much more complicated and involved than it would be with a CNF, which is just a list of lists in the most straightforward way, and therefore it's much more expensive to keep this data structure up to date when simplifications are performed, when modifications have to be done in order to assign values and so on. And the other problem is that on the one hand there are simplifications, so techniques that modify the formula in a way that the truth value remains the same, so it stays satisfiable or unsatisfiable, but such that it becomes easier to solve. Yeah? And such simplification techniques often affect only subtrees when the formula is represented as a tree and not the overall formula, and they do not propagate to the top level, and therefore it can be that the simplification does not help too much. And it would be much more powerful if applied on a CNF where, for example, if a contradiction on a part of the formula can be derived, then it can be immediately decided that the formula is unsatisfiable. Yeah, this is one thing. And on the other hand, there are techniques that work only on Cnf formulas, and therefore it would be good to have such a representation. And the idea is now not to work on the formula in arbitrary structure, to have a formula with these three structures, but to transform the formula into a normal form and use this formula in normal form as input for the SAT solver, such that the SAT solver can exploit the nice properties of the normal form. And we discussed CNF and DNF, conjunctive normal form and disjunctive normal form. Remember, a formula in conjunctive normal form was as follows. So we have a conjunction of clauses. A clause is a disjunction of literals, and a literal is a variable, a negated variable, a truth constant, or a negated truth constant. Yeah, so a CNF can be represented as a list of lists. We have a list of clauses, and a clause is also a list of literals. Or a DNF, which is another normal form, which is the dual variant of a CNF, a disjunctive normal form. There we have a disjunction of cubes, and a cube is a conjunction of literals. Yeah, and the question is what formula should we use? And we could use if we would have a formula in disjunctive normal form, then solving the satisfiability problem would be extremely easy. Yeah, then we just have to look if all cubes are not contradictionary, yeah, because a contradictionary cube is immediately false. And if this is not the case, we immediately know that the formula is satisfiable, and in order to get a satisfying assignment, we just have to look at one cube, and this gives us a satisfying assignment. Let us look as an example. I switch to my writing space. Here I have an example of a formula in DNF. On the top level we have the disjunction symbol, and these disjunctions connect cubes. So we have 3 cubes, cube 1, cube 2, and cube 3. And when we look at the cubes, then here in this cube 2 we have a contradiction. We have not A and A, so this cube is obviously unsat. Yeah, therefore we do not have to consider it further. But in cube C1 and in cube C3 we do not have a contradiction, and what we get are 2 complete satisfying assignment. So assuming we have a formula just over variables A, B, and C, and the first satisfying assignment, let's call it sigma 1, is simply A, B, C. Recall, I write a satisfying assignment as a set of literals. If the positive literal is included, meaning that the literal is not negated, then it means the variable is set to true. If the negative literal is included, it is set to false. Yeah? And if we have this assignment sigma 1 containing the variables A, B, and C, then this means all 3 variables are set to true. If all 3 variables are set to true, then C1 is true under sigma 1, and with this we can conclude, let's call the formula phi, that phi is true under sigma 1. And the same for the assignment we get from cube 3. Let's say, so this comes from here, from C1, and from C3 we get a satisfying assignment A, B not C. Yeah, so we really just read off the literals. Then we know that C3 is true under sigma 2. And then we can conclude that phi is true under sigma 2. And sigma 2, yeah, we got from this cube C3. Okay? And therefore, deciding satisfiability of a formula in DNF is really easy. And so we could say, okay, why don't we transform the formula into DNF and then just read off if it's satisfiable or not. Yeah, the problem is that the translation into the DNF is not easy. So there is no efficient algorithm known to obtain the DNF. In the worst case, we have an exponential blow-up with the known algorithms. Okay, so we cannot use the trick to transform a formula into DNF and then read off the value of the satisfiability status of the formula. This doesn't work because the translation into DNF is expensive. Now let's have a look at the Cnf formula, a formula or the representation in conjunctive normal form. If we have a formula in conjunctive normal form, it's very easy to find a counterexample. Yeah, we can easily say, okay, we have here this disjunction of literals, and if we set all these literals to false, then we have a counterexample to the formula. But the satisfiability problem is not easy to solve. Yeah, here in the worst case, with the known algorithms, we have to consider this exponentially many candidates of assignments that could satisfy in principle the formula. And now the good thing is that Cnf can be efficiently calculated. There is a trick, and this trick I would like to show you in the following. But before we do so, let's have again a look at the writing space and at some example of a Cnf formula. Here we have the formula psi in Cnf. Yeah, it's a different formula than the formula we considered for the DNF. So this is just another independent example. And this formula consists of 3 clauses. Yeah? So we have clause 1, clause 2, and clause 3. And in clause 2, we have A and not A, and this means here we have a tautology. This means that this formula, this clause is always true, yeah, because we have A or not A in there. So therefore we can immediately skip it. It will not help us to satisfy the formula, and we have to consider only clause 1 and clause 3. If we consider an assignment sigma, or let's call it now tau, to indicate that it's different one than before, tau 1 is not A, not B, not C, yeah, then clause 1 is false under tau 1. And therefore psi is false under tau 1. Yeah? So we can immediately read off a counterexample from a formula in Cnf. To find a satisfying assignment is more complicated. In this case, it's not so complicated because we see, okay, there is an A, and in this clause is also an A and there are no other occurrences of A, so any assignment where A is set to true is a satisfying assignment of this formula, because it satisfies this clause and it satisfies this clause, and therefore we can conclude that psi is satisfiable. But in general it's not so easy, and much more effort will be necessary, as we will see. Okay, and in the following I will explain you how to obtain Cnf for a given formula in arbitrary structure. Okay, so how can we get the formula in Cnf? First approach is to use the rewriting rules we have seen before. So we have had a lot of equivalences that we now can use in order to rewrite a formula such that it becomes an equivalent formula in Cnf. So in the first step we have to remove all symbols that are not conjunctions, disjunctions and negation symbols. So for example, when we have implication, equivalence and XOR, we can use the following rewritings. Phi implies psi is the same as not phi or psi. Then if we have phi is equivalent to psi, then this is the same as phi implies psi and psi implies phi. So we have here twice implications introduced, which we can then rewrite. And for the XOR, we simply replace this by the formula not phi is equivalent to psi. So if we have phi XOR psi, this is equivalent to not phi is equivalent to psi. Yeah? And then we can eliminate the equivalence by the implications, and the implications can rewrite as we have seen before. And it's very easy to show that these equivalences hold. We just have to do a truth table and can show that these formulas we have here are indeed equivalent. Okay, and if we have eliminated all the symbols that are not disjunction, conjunction and disjunction, we can go to the next phase where we transform the given formula into a formula in negation normal form. What we do then is we apply the laws of De Morgan, and we do so in order to shift negation symbols inside of the formula, such that at the end negation symbols occur only in front of variables and truth constants. And if we have the situation that two negation symbols meet each other, then what we do is we eliminate them, because if we have something like not phi, then this is the same as phi. Okay, and when we have this negation normal form representation, we can transform the formula into Cnf by using distributivity. Okay, so here I have an example. We have not A is equivalent to B. This not binds very strong, so it belongs here to this equivalence in front of, so it belongs to this equivalence. So this not A equivalent B implies not C and D and E. So in the first step, what we do is we remove the equivalence by using this rewriting we have seen before, and get A implies B and B implies A. The rest of the formula remains unchanged. In the next step, we eliminate the implication symbols. Yeah? So we have 3 implication symbols which we eliminate. We can do this in multiple steps, but I did this only in one step. So A implies B is the same as not A or B. Then a B implies A is not B or A. And here then we have this implication symbol. We introduce an other negation symbol and replace the implication symbol by a disjunction. Yeah? So the left hand side of the implication is negated and the implication operator is replaced by a disjunction. With this, we have a formula that contains only disjunction, conjunctions, and negation symbols and variables. And in the next step, we transform the formula into negation normal form. What do we have to do? Here we have the situation that we have two negations. Here we have the situation that we have two negation symbols next to each other. We eliminate those, so they simply go away. That's very easy. And then we have to look where else do we have negations, and here we have a negation that is in front of a formula that is not a variable or a truth constant. And what we have to do is we have to apply De Morgan, shift the negation inside, and we get here not C or not D, so the conjunction here becomes a disjunction. So this was all that was necessary to obtain the formula in negation normal form. All the other negation symbols are in front of variables, and therefore no further actions are necessary. And in the last step, this is usually the most complicated one, when done by hand, we have to apply distributivity in order to obtain formula in conjunctive normal form. So we have to look where is a problem. Here we have, here it would be useful to draw the tree. Here we have disjunction at the top level, and we want to have conjunctions at the top level. And what we have to do is we have to multiply this out. So we have not A or B, or, and this formula here, and we have not B or A, or this formula here. And then now we have here at the top level a conjunction, and so when we look, we have to check what else do we have to do, and finally we have to multiply out the rest, and then we get this formula here. I can do this at my writing space. What we want to do is to get from this formula here to this formula here, and I will show you how to get from this formula part to this formula part here. The other side works similar. So we have not A or B, or not C or not D, and E. And this is now the same as not A or B, or not C or not D, and not A or B, or E. And this is now the same as not A or B, or not C or not D, and not A or B or E. Okay, so this is the reason, or the justification of the first two clauses, and the other two clauses are obtained in a similar way. And this is how we can obtain the conjunctive normal form by using multiplication. There is a major problem, and the problem comes from the blow up which we can get. Consider, for example, a formula A and B, or C and D, or E and F, something like that. Yeah, I will not show it to you in general, but only the problem we get. Yeah, when we have this formula and we want to multiply it out, then what do we have to do? Now, yeah, we have to do the following. We have to duplicate the A and B and get A and B or C and A and B or D, yeah, and then we put big parentheses around it, and or E and F. Yeah? And what we now have is we have now duplicated the A and B. Okay, so this occurs now twice in the formula. What we now have to do is we have to shift the C inside. We get A or C and B or C and A or D and B or D. But unfortunately we are not done. What we have here is on the top level still a disjunction, and we have this E and F. Yeah? And now when I do not want to write this down, but when we now multiply this out, then we suddenly have 4 copies of the E and F. And this would consider with every cube which we had in order to transform the formula. Yeah, this would continue with every cube we have when we transform the formula. And therefore the problem is that when we have a formula in DNF and want to write it into a CNF with this approach I just showed you, then we have an exponential blow up, and this is not good. This is in fact really problematic. When we have an exponential blow up, then we quickly run out of resources, and we have to find a way of doing it better, and this I will show you next. The idea to solve this problem is a trick that is quite generally applicable, and the trick is to introduce names for the parts of the formula. So we have X here, for example, we have Y here, and we have Z here, and we say we have a clause X or Y or Z, and then we have to define X and Y and Z, and we say X is equivalent to A and B, and Y is equivalent to C and D, and Z is equivalent to E and F. Yeah, so if we use this trick, we still have to transform these parts here into CNF, what we then can do by this approach 1, which I have just shown you, by first replacing the equivalence symbol and then rewriting the formulas just that we get a set of clauses. But here we do not have the problem as before, because we have one side of this equivalent symbol which is just a variable. Yeah? So here we do not have any other complicated formula. And let's do it just for this one here. We have X implies A and B, and A and B implies X, and now we can easily rewrite this to the following formula. We have not X or A and B, and not A and B or X. And now we're almost done. We have not X or A. We have and not X or B, and not here I did a mistake. We have not A or not B or X. Yeah, so overall for this one definition here, I just get 3 clauses, 3 small clauses, 2 clauses of size 2, 1 clause of size 3, and not more. It cannot be more. Yeah, and so we have a way of translating this formula into a CNF formula without duplicating parts of the formula. And the trick is to introduce novel variables that abbreviate subformulas of the formula. This has a price to pay, as we will see, but let's first generally introduce this approach. We are given a formula phi, and we use the following approach to transform phi into an equisatisfiable formula in CNF. I will explain later what this equisatisfiable means. This is actually the price to pay, which I mentioned before. So for each subformula that occurs in phi, we introduce a label. Yeah, we have seen techniques, or we have seen how to find the subformulas of a formula, and now we use this splitting of a formula into subformulas for the CNF transformation. Yeah, so for each subformula we introduce a label. For each subformula that is not a literal or a truth constant, we introduce this label. Then we do the following. We replace also in the definitions complicated formulas by their labels, which we have identified. And so for each label we obtain a definition of the formula of the formula which we obtain by replacing the subformulas by label. Yeah, so we do not have any deep formulas anymore, but we just have these flat formulas, and this helps us to avoid the blow up as well. Yeah, and then we have this collection of all definitions, and transform this formula with the definitions into CNF by the approach we have seen before. And then when we have this formula where the definitions are translated into CNF and the top level label, we obtain a formula that is equisatisfiable to the original formula. Now, what does this equisatisfiable mean? It means that if the original formula is satisfiable, also the formula in CNF is satisfiable. If the original formula is unsatisfiable, then also the formula in CNF is unsatisfiable. This is a bit of a weaker notion of satisfiability of equivalence as we had it before with the semantical equivalence. For the semantical equivalence, we required that two formulas have exactly the same models. Since we are introducing new variables here, this is not the case anymore. We can easily find a model that is we can easily find an assignment that is a model of the one formula but not of the other formula. But we know that if the one formula is satisfiable, also the other formula is satisfiable, and vice versa. So it's not a problem if we now then solve the formula in CNF, because we know, and this can be proven, that the formula is satisfiable if and only if the original formula is satisfiable. Now let's have a look at an example. we have the example from before, and here I have a list of the definitions. First, we replace A is equivalent by B by label V1. Then we replace the formula not V1 by label V2. Yeah, so this is this subformula here. Then we have a look at here at the subformula C and D. This we give the name V3. For V4 we have the formula not V3. This is this part here. And then for V5 we have V4 and E. This is this part here. And then finally we have V6, which is the label for the whole formula, and there we have V2 implies V5. Yeah? And here we have the clauses we obtain when we translate all these definitions into clausal form, and the conjunction of these clauses together with the unit literal V6, with the unit clause V6 at the top level gives us equisatisfiable representation of the formula phi. Yeah, and yeah, that's the basic idea. Yeah, so we replace subformulas by labels, we define the labels accordingly, and then we get a formula which can be easily transformed into Cnf, because we do not have any involved nestings of formulas, and then we get a equisatisfiable formula in Cnf. And now the question is, why is this not semantically equivalent? I will show you an example, therefore I will switch to my writing space. Say we have the formula A and B or C, which is obviously not in Cnf. So what we do is we introduce an X for A and B, and for the whole formula we introduce a Y. So X is equivalent to A and B, and Y is equivalent to X or C. Okay, and now we have to get the following formula. We have Y, which is the top level symbol, and then I get the clauses for these two formulas. We have not X and A, or A, sorry, and not X or B, and not A or not B or X, and then we have not Y or X or C, and not X or Y and not X or C. Yeah, so this is our formula in Cnf. And now what would be an example? Say we have an assignment A, B, C, not Y. Yeah. Then let's call this phi, and this is phi Cnf. Then what holds? Phi Cnf is false under sigma, but phi is true under sigma. Yeah? Because A and B and C are all true. This makes this phi formula true, but Y is false, and therefore phi CNF is false. So this means we found an assignment under which the formulas have different truth values. However, if we would have an assignment where y is true, then also phi CNF would be true, and we would and therefore we see that phi CNF is also satisfiable. Yeah. So under tau, let's say we have an assignment tau, which is A, B, C, Y. This is an assignment that phi CNF is true under tau. Yeah. So this is a satisfying assignment of phi CNF as well. But the important thing is that not all assignments satisfy or have the result in the same truth value of the formulas. Yeah, so there might be assignments which make one formula true and the other one false. The important thing is that if the one formula is satisfiable, also the other formula is satisfiable. And with this, we have a very powerful tool and a very efficient tool of translating formulas into CNF, and then we can exploit this CNF structure for solving propositional formulas, and this is what I will show you next. To sum up, we have seen two approaches to obtain a formula in conjunctive normal form. The first approach uses equivalence preserving rewritings, but it is exponential in the worst case. Here we have an example which is problematic. Then we have a polynomial approach, where the basic idea is to introduce labels for subformulas, and this was just the core idea. There are several improvements and optimizations. For example, if a subformula occurs multiple times, then the label can be reused, so the definition doesn't have to be introduced several times. This approach is also known as Zitten encoding. There is another optimization which is called Blested-Greenbaum, and this one reduces the size of the definitions by analyzing in which polarity a subformula occurs, so if it's negative or not, and then one direction of the implication can be omitted. Yeah, when we have a CNF, then we have a formula that is usually not easier to solve, but it is easier to handle. We have compact data structures for such formulas, and then we can apply certain optimizations which do not work on general structured formulas. Finally, CNF is very popular in practice. The standard input format for SAT solving is in Dimax, so usually SAT solver do not support the Limbool format that we use in this course, but there is something called Dimax format, and here we have a textual format which contains one clause per line, and the literals are integers. If they're positive, then they're not negated. If they're negative, this indicates negation. And now we will really have a look how CNF formulas can be solved. And for this purpose, we will look at a very old algorithm which is called Dpl. It is named after its inventors, which were Davis, Batman, Loveland, and Lodgman. The algorithm is really old. It was invented in 1962, and back then it was by far not clear about which impact it will have. And as you will see, it's a very, very easy algorithm. The pseudocode is very small, and it's also very well investigated, also very well understood. It works in general for formulas in CNF, and one of the powerful techniques that it uses is binary constraint propagation, which we will have a look at in the following. And it is in the way it is originally presented, it's not implemented in modern SAT solvers, but it's the basis for it. And in its modern form, it's implemented in an approach which is called conflict-driven clause learning, and this is used in almost all SAT solvers. In this lecture, we will not talk about conflict-driven clause learning because it requires a bit more background, but later on in your elective courses, you can have a dedicated course, SAT solving, and there we will see how CDCL, conflict-driven clause learning, works. So, but first of all, let us have a look how PCP work. Assume we have a formula in CNF and there is a unit clause. A unit clause, remember, is a clause of size 1, so it is a clause that contains exactly one literal. And if we apply PCP, then we remove all clauses with this literal, and then we remove all occurrences of the negation of the literal. Yeah? What does it mean? It means that if we have a clause of size 1, we are forced to set the value of the literal respectively. Yeah? So, for example, if we have here in this formula we have a clause that contains just the variable a, yeah, then we immediately know we have to set this a to true, otherwise the formula would evaluate to false. It's very easy to show that any satisfying assignment of this formula needs to have a set to true, otherwise it is false. Yeah. Then we can propagate it by we can propagate this decision. We set a to true, meaning that we remove all clauses with a, because if we have a clause with a, then the clause becomes true. If we set a to true, so this clause goes away and the unit clause goes away, and in all clauses containing not a, we remove the not a, because a is set to true. This means not a becomes false, and we become the simplified clauses b or not c as a first clause and not b as a second clause. Now the second clause, not b, is a unit clause. Yeah? So here we have a clause of size 1. What do we do now? Now we set this clause of size 1, we set the literal in this unit clause respectively. Yeah? Not b means we have to set b to false, otherwise the formula is false, and if we set not b to false, then the unit clause goes away, and we remove the b here from this first clause, and we get a simplified formula not c. And if we have a simplified formula not c, then this not c here is again a unit clause, and we set c to false, so not c becomes true. Then the CNF becomes true, and we can immediately decide that the whole formula is true. Yeah? So by just applying PCP, we could decide that the formula is true, and no further steps were necessary. No further assignment of the variables were necessary. Yeah, this is a very simple technique, but extremely powerful. And what we have seen is that the application of one propagation of a value can trigger the application of another. So that what we have seen is that one application of PCP can trigger the application of of PCB on another variable. Yeah, and when the formula becomes empty by PCB, so if PCB produces the empty Cnf, we know that the formula is satisfiable. If PCB produces the empty clause, then we know that the formula is unsatisfiable, and for this I will show you another example. So assume we have this formula phi here given, and we have this unit clause that contains not C. Yeah, I use the over line to indicate that the variable is negated. First I calculate PCB of phi and not C, and this is then phi prime, and what we get is A or B and not A or B and not B. Yeah? So we have to set C to false, then the C here goes away and we get a new unit clause not B. Then we calculate PCB of the new formula, and we get A and not A, because here we set B to false, and therefore in the first clause the B goes away, and also in the second clause the B goes away. And now we have the choice, we can set either A to true or to false, because we have two unit clauses, doesn't matter. Say we set A to true, and now we do not get the empty formula, but what we get is the empty clause, because we remove this clause here, yeah, and we remove this literal, and so we have the empty clause, and the empty clause is bottom. Yeah, so as soon as we have a Cnf formula with the empty clause, then the formula is unsatisfiable, and therefore we could show that the Cnf that we considered is unsatisfiable. The slide here shows the full Dpl algorithm. The input is a formula in Cnf, we call the formula phi, and the algorithm returns 1 if and only if the formula is satisfiable, otherwise it returns 0. On the top level we have an infinite loop, this is while true. We do the following, and we have some conditions that allow us to quit this infinite loop and to return. Yeah, and one condition is that the formula is has become empty, then we return 1. If the formula contains the empty clause and no further option is possible, then we return 0. Okay, but let's first have a look how this algorithm evaluates the formula and iterates over all possible assignments. So first, the formula is simplified by PCB. We have no second argument for PCB. This means PCB is applied until fixed point. If the formula that we obtain is stop, it means it becomes empty, then we return 1. If the formula becomes bottom, if this means it contains the empty clause, then we have to do several things depending on whether there are further options or not. But let's assume the formula is not empty. Yeah, this means the formula maybe simplifies, but we cannot decide the truth value. What we do now is we select a literal that occurs in the formula and add this literal conjunctively to the formula. If we add a unit clause with this one literal to the formula, then in the next round, when we perform PCB, the variable of the literal is forced to the respective value. If the literal is positive, then the variable the literal contains is set to true, If the literal is negative, then the respective variable is set to false. Yeah, assume L is the variable x, then the value of x is set respectively. And what we also have to do is we have to store the status of the formula on the one hand, and we have to store which value of the literal we did not consider. Yeah, and for this purpose we use a stack. A stack is a very simple and basic data structure which has only a few operations. So on the one hand we can push data on the stack, and then later on we can pop data from the stack. And a stack is the so-called LIFO data structure. This means last in, first out. And the element that is shortest on the stack is popped first. Yeah, so if we call pop, then we take an element from the stack, and the element we take is the topmost. And if we call push, we put some element on the stack and put it on the top. So we create a stack. Yeah, you can imagine it like a sheet, a stack of papers. The oldest is down on the lowest level, and then whenever we add a sheet of paper, it is put on the top, and when we take it, when we want to take something from the stack of papers, we take the topmost. Yeah, and so what we do here is we push the formula in order to store the value of the formula, and we store which value of the literal we have not considered, so we push the negation of it. Yeah, and in a later round, when the simplification by PCB resulted in a formula with the empty clause, we have to check if the stack is empty. If the stack is empty, this means we have all possible assignments considered. Yeah, and therefore we return 0, which means that the formula is unsatisfiable. Otherwise, we pop the topmost element from the stack, which gives us the status of the formula where we haven't set L, the variable of L, and now we set it, and then we proceed. Yeah, and so we can iterate over all possible assignments, and by using PCB we can perform some pruning and do not have to take care of literals that are somehow implied. So their values are forced by PCB, and so we not necessarily have to iterate over all variables. I would like now show you an example. For this purpose, I switch to my writing space. We want to solve this formula phi 0 here, which consists of a couple of clauses. And in the beginning, the stack is empty. Yeah? So here we have the stack. And we apply now the Dpl algorithm to solve this formula. In order to distinguish the formulas, I give them an index. This makes it a bit clearer. So in round 1, we get phi 1, which is PCB of phi 0. And this is simply phi 0 because we do not have any unit clause here. So the formula phi 1 is different from top, and it's different from bottom. It does not contain the empty clause. Therefore, we pick a literal, and yeah, I just pick literal A. Yeah, and now I put phi 1 on the stack and not A. Okay, good. And I update phi 1 and say phi 1 is phi 1 and A. In first iteration done. In round 2, I calculate phi 2, which is PCP. Let's call this phi 1 prime, which is PCP. Phi 2 is PCP of phi 1 prime. And now there is a unit clause which contains A, so A is set to true. I do it rather quickly. We get B not B, so the first clause goes away. The second clause simplifies to not B. Then we have not C or B because there is no A. Then this clause simplifies to B, and this clause goes away. And now we have two unit clauses, not B and B, and we immediately see this formula is bottom. Okay? So phi 2 is bottom. Stack is not empty. So what we do now is we pop the content from the stack in order to obtain phi 2 prime, and this is now the formula on the stack and the literal on the stack, not A. Okay, so and the stack becomes empty. And now we have phi 2 prime, which is phi 1 and not A. Phi 1 is as defined above here. This is the reason, in order to avoid confusion, I introduced the primed variant. So we are now in round 3. In round 3 we have phi 3, which is PCP of phi 2 prime. This is phi 1 and not A, so we get B or C, and now the second clause goes away. We have then not C or B. Then this clause, this clause not A or B goes away, and we have a clause not B. Okay, now we have another unit clause here, which is not B. So we can further simplify the formula and we get C and not C, and this is bottom. So phi 3 is bottom, and stack is now empty. Therefore we can conclude phi 0 is answered. Yeah, because we have no further option what we could try. We tried both values of A. We set A to true and we set A to false, and in both cases it happened that the formula became answered. In both cases the formula evaluated to false, and there is no other value which we can try for A, and therefore we are done. Yeah, and with this we have illustrated how PCP helps to solve a formula. So we did by far not try all possible combinations of the values to A, B and C, and this gives the power of Dpl. Okay, so here I have some further remarks on DPL. It's the basis for most state-of-the-art SAT solvers. Some recent SAT solvers which were developed by Professor Biere back then when he was in Linz are Lingeling, Cadicle, and more recent one is KissSat. You find them all on the internet. And what is important is that DPL alone is not enough. There are very powerful optimizations which are required, and these include learning and non-chronological backtracking, which I mentioned before. This is the CDCL, and reset strategies facing very special data structure. So then this selection of the literals has to be done in a very careful way, and then there are a lot of other techniques often related to resolution which has to be applied and which are indispensable for getting a result. We are still solving a problem that is NP hard, meaning that in the worst case we have exponentially many possibilities to consider, and only with clever techniques we can avoid this. And Dpl is also the basis for solving in other logics, for example in QBF, which is an extension with quantifiers, which we will not cover in this course, but also for satisfiability modulo theory, which we will discover in the last 2 units, and which heavily relies on this approach. Therefore, I wanted to show it to you. And a major challenge in SAT solving is how to parallelize this approach. It's not entirely clear, but there are some successful attempts in the solvers which are listed here, and with this it becomes indeed possible to solve hard problems exploiting modern hardware. With this I will conclude this lecture. Thank you very much for watching.